difficulty in hearing me, then let me know. Then I will pick it up. அது தெரியல. இருக்க முடியாது. கொஞ்சம் இந்த மாதிரி
Hello. Sorry for the delay in starting this program. This is what's the number? 74?
73, I think.
74.
74?
Okay, 74th lecture of the Popular Science Lectures series of Tamil Nadu Science Forum, Madras, South Madras chapter. We are doing this. There is any problem with English? Let me know. I think all of you will be familiar with it. So if you have, we have been doing this for the past 5 days. We knew the science work was started in 1881. And the only claim to be this one of student who played in the role in starting the science work. After that, it has taken off in various activities. Taking science to all the sections of people. We played a major role in Arivoli Iyakkam, which is actually a literacy program, taking to the rural areas, other places, etc. And we have also had several interventional programs like look at environment questions and play some role, get some scientists to bring out some material on various issues of this kind. Several. Don't want to go on boasting about it. But these are the things we also run for children up to something like 8th standard. A Tamil magazine called Tulip, which is actually popular. And thanks to several Tamil Nadu governments, we have been able to send it to several schools and a lot of students, young students. Parents are very keen that the young boys or girls, they read those things. Also, we have a slightly higher level on the middle school, which is in English also, called Jantar Mantar. So, which is also slightly popular. The whole idea is to take it even further, the college level and beyond. And these science lecture programs are mostly tuned to generally slightly advanced levels, and a lot of people do take part. I have another page. I was the first person to give a lecture because nobody else will give. So in 2018, when acting after Hawking's death, I did give a talk, the first lecture PSL 1, what is called PSL 1, in the same hall but downstairs. Your big hall which is there, auditorium. And since it was the first time it was starting and many people were interested, if I tell you, you will not believe me, it's true, it was attended by about 400. The whole hall was full. And of course, Murugan is here. He was also one of the speakers at that time. So this kind of program from that time we took off and various places. But during COVID, we have to make a new change. And that was the first lesson for us that we should use more modern things. And we started doing online activities. Lectures were organized, for several lectures were organized online. Then after the COVID situations were over, we started with meetings.
Vijayan's thing is showing up in order. Can you suppress that?
It's the modern given.
Yes.
YouTube.
It's suppressed.
So that is the way we started. We had a difficult. The students and youngsters who were in Chennai were attending earlier. Now they say, okay, I'll listen to that in Zoom. So our participation in actual here kind of place is slightly less. Actually, people should realize that if it is offline meeting, it is first of all very good because you are going to see the speaker. But after the question and answer session, and then you can privately meet the person for some more time. Usually they are very considerate. And yes, Viswanathan is going to speak. It's extremely considerate. So this is a kind of an advantage of offline meetings. And, but one thing is when we started online program and registrations, etc., we have a list of about 5,000 people who are registered for our programs. They join in several times. It will not be immediately. And they join over a period of time and see in YouTube, etc. This is what the success of this program. And thanks to the library, thanks to the library, we have been utilizing their services, their places quite elaborately on many occasions. I should thank them because there are few places where we use. One is this place. Another is my own institute, called Institute of Mathematical Sciences in Taranani. I'm from that place. And IIT Madras. These are the three places, and also University of Madras also has given this thing, the hall and facilities. So we have utilized. But most of the time it is only this place and my own institute, where we can have a hall free for us. People can come easily and reach the place and take part in the program. So this is our further introduction to Science Forum is concerned. Now, if any of you are interested in taking part in this program, there's Uber there, Aditya Verma is there, and bank officer, right? Yes. Yes, he was in State Bank. Yes. Yeah, he was in State Bank officer, now retired, like me as a was. So people can contact us so that we'll put you in the list. And also, if there is any way you can contribute in identifying people, taking the program further, all the places will make it useful to us. So that is as far as Science Forum is concerned. Now, the speaker is a good friend of mine. I've been following him for a couple of decades, and I knew him when he was in Anjika, Pakam, here. I used to work here. So he was a chemistry person and physics person. So a lot of interesting people I used to meet from Ajika, and he was one of them. Then he decided he would shift to IISER Mohali. And I didn't leave him, I went and saw him there. And I had breakfast with him. And well, I did do somehow there, which is that occasion I met him. And then that's not enough. I decided to follow him even further. He is now associated with Krea University in SriCity, which is just on the outskirts of Chennai. And I also go there. And both of us are visiting professors there. We give lectures, we discuss, we chat with various people. And it is an interesting journey we have been having together. And he is an excellent speaker, teacher, and he impresses. In fact, he does magic also with chemistry. The last thing we did was on several magics in the room here downstairs. Now he has decided that science is a little more than what we do in the lab. What we do in that, with all passion, etc., accidents do happen. And those accidents sometimes lead to better science also. You expect something, it doesn't happen. Something of that is there. And of course, science is learn something from theory, something from practice. Nature is always telling you what is happening, etc. It's extremely mind-boggling activity which is going on. Now, after all the thing I learned, all the elements which I know everywhere, including whatever I'm using, they were all produced in the interspace by stars. Not here. They were produced there. So these are all very impressive things which have happened in several areas of science. And modern science and technology has taken so much that what I learned in my college days is nothing. And so much changes have taken place. And we should be prepared. For me, I'm as good as I would like to learn from him later. When he becomes king, he will be producing new ideas. Like that, it is always happening. And this is the kind of a thing about science. And he's going to talk to about the title Serendipity. And as you know, there are accidents happen, and then people didn't expect and happens. And immediately they don't put their hand, what they have, I lost $1 million, something like that. They try to find out why it is happening, how is it happening, and new things, and that leads to science, new sciences. So that I'm going to stop, and I hope. Are you ready? Okay, I will hand over to. Yes.
Yeah.
Okay.
You have a pointer?
Thank you.
Point.
Working, but it's not having work.
Oh, no, but just oh, okay. Okay.
What is you on the mobile? Yeah.
No, I'll just use my hand. It's all right.
Okay.
Thank you very much. Thank you for the introduction. Thank you to the Science Foundation for having me over so that I can talk to you. Thank you all for coming, because nothing is more reassuring than to see a lot of people, wanting to listen to you. And a big thanks to the library, because I think they've done a great organization out here. And it's also very interesting to see that they have the relevant books.
On I put off and down. Off and down. Okay.
Fine. Yeah. Accidents do happen. So, and so a big thanks to the library, that they're very thoughtful of them. They have all the books on serendipity put out here. So after the talk, if you think you need to learn a lot more or check certain things out, what I said, I think you have all the information here. That's very nice of them. A big thank you to you all. What I will do today is to recount some of the very interesting accidents that happen in labs. And mind you, in labs, when we go in to do experiments, very often we have a certain idea of what we are planning to do. But it's not always that, and thankfully, it's not always that you see what you expect to happen. And that is when research becomes extremely interesting. I'm going to recount some of these incidents. There are many more. I'll just recount some for want of time. But the idea I want to drive home is that it's always important in the lab when you work to keep your eyes, ears wide open to see anything that might pop up, which is totally unexpected. And that's basically the whole point. Before that, let us try to understand how does scientific progress actually happen? It's important to understand the process of scientific research. Next slide. There's no way I can control from here. So we will talk about how scientific research is actually done, the methodology of science, and then we will go on to looking at the very interesting accidents, which has actually catapulted people to fame based on these accidents. And I will just recount about 3 or 4 such incidents, which will be of interest to you. Yeah.
Doesn't go back, but
It'll go back.
okay.
It does go back. It just takes time.
Okay.
Yeah. And in this whole process of scientific progress, just doesn't.
Next slide.
And accidents in science, as I said, has a certain relevance, has a huge relevance in the whole process of scientific growth. Now, what is the scientific process? The scientific process is the ability to observe. It's very important to be able to observe very keenly. The ability to observe, the ability to formulate an hypothesis based on your observation. You look at the observation that you have had, and then you come up with a hypothesis. And the ability to do so is an extremely important aspect of science. Ability to design fresh experiments to check out what you have just hypothesized. Ability to construct arguments, very relevant and very convincing arguments, and to develop a very critical and analytical rigor in the whole thought process. So these above processes actually are very important in the contribution to scientific research. Of course, this is not only in scientific research, the very same characteristics or the very same attributes are required for us in everyday life. So every time we are faced with a problem, mind you, we have to employ this methodology to solving it. And therefore, the method of science is not just practiced by scientists, it is also practiced by people at large in normal everyday life. But we just call it as a scientific progress because it is sort of well categorized in the scientific methodology. What is the scientific methodology? I'll just put a little flow sheet out here for you. The scientific methodology, the thing it happens is first you identify a problem to study. You say, look, I want to study the property of something. So you identify the problem and then you propose an experiment to study it. So after the experiment is performed, you perform the experiments and you make observations. That's what I said earlier, the ability to observe. Very, very crucial. And once you have made the observations, you have then come up with a hypothesis to explain the observation that you have just made. That's not enough because you have to now use your hypothesis and make some predictions. If my hypothesis is true, then the following should also happen. Then do further experiments to check if the consequences of your hypothesis are borne out. If it happens right, then your hypothesis is probably right. I'm not saying it is right, it is probably right. And you can do more cross-checks to see if your hypothesis is right. But supposing it doesn't turn out that way, you have made some predictions based on your hypothesis, and it turns out that those predictions are not borne out by future experiments, then it either means that your hypothesis is wrong, in which case you go back and come up with a new hypothesis, or it could mean that your experiment was wrongly done in the first place, and therefore you got to go back and check your experiments. And then the cycle starts. This is basically the scientific methodology. Identify a problem, do an experiment, observation, hypothesis, check your hypothesis. If it is right, you keep going further. If it doesn't turn out that way, alter your hypothesis or redo your experiments. So this is what a scientist almost always does. Not explicitly, but at the background, this is the process. This is a flow sheet that is obviously used by all scientists. Let's see. But the important characteristics in formulating a hypothesis, mind you, whenever you formulate an hypothesis, it has to have one important characteristic, namely that your hypothesis must be so formulated that you can either verify it to be right or you should be able to falsify it. Your hypothesis must be stated that way. What do I mean by that? That's a Popper's falsification principle in scientific philosophy. The hypothesis is firmly tested by a falsification process rather than by a verification, very often. What does that mean? If I have a theory, I do experiments, and my experiments say, it agrees with the hypothesis, with the existing theory, what will your paper look like? I have done these following experiments, and it is in agreement with theory. Not interesting. Easy to publish, but not interesting. But supposing you do experiment and it turns out that your hypothesis, your experiments are pointing to the fact that the existing theory is not right or is inadequate, then you have broken new ground. Very hard to publish such papers because anytime you falsify an existing theory, the referees are not going to leave you alone very easily. It's very hard to publish, but that is where you break new ground in science. And your theory must be so stated that you can either verify it to be true or verify it to be checked to be false. This falsification aspect is extremely important in any scientific hypothesis. If I make a very vague statement that can never be falsified, it's not a scientific theory at all. And we will see what that really means. If it is so stated that you can never falsify it, into the garbage. That's not a scientific theory at all. And in fact, as I said, you break new ground when you falsify an existing theory based on your experiments. Let us consider two reliable scientific theories which were so formulated so as to be subjected to this falsification process and see what went on. The first one is Einstein's general theory of relativity. You want details of general theory of relativity? I'm not the person. The person is sitting right here. But we will see what actually happened during that time. Einstein's general theory of relativity was talking about the effect of massive bodies on light, that the gravitational forces can actually bend light. And that was something that he had proposed in his general theory of relativity. After the special theory first, then came this. Now, the point is this. can this theory be proven? Meaning, does gravity or massive bodies, do they really bend light because of the gravitational forces? Can you bend them? Now, the experiment has to be done in such a way either to prove that Einstein was right or to prove that Einstein was wrong. Now, theory was stated very clearly, so he could actually check for its verification or falsification. How can you do that? That's of course Einstein. What the experiment that was devised was the following. Here, of course, if you want to talk about massive bodies, sun is a massive body. So any light that goes close to the sun, if Einstein's general theory was right, should bend. If it bends, see what happens. So if there's a star out here and the light from the star is moving in this direction, the sun would bend it, and on the earth you would see it here. But what would you think? You think the star is actually here. So you would get this illusion the star is there. In other words, the sun has basically deflected the apparent location of that star. If Einstein was right, you should be able to see that displacement. If Einstein's theory was wrong and that there was no effect of massive bodies on light, then you wouldn't see it. So the theory was stated well enough to be either checked or falsified. Now the question was, how do we do this experiment? What's the problem in this experiment? Well, I have to see a star behind the sun.
It cannot be done in Earth.
Pardon?
It cannot be done here. Actually, it's about space.
I know, but why can't you see? We can see stars. Why can't we see the star behind the sun? Because the sun is so bright, you're not going to be able to see. Even if the star had moved its apparent position here, with the sun sitting there, you're not going to be able to see that star. So what's the best time to see the star? Total solar eclipse. Sun is still there, but there's no light. So now you have to wait for the total solar eclipse to check this out. Einstein was lucky in that sense. He had proposed this, I think, 1911, 1912, but he had made a mistake in his calculation, and he had shown a certain displacement, which was wrong. But luckily for him, the total solar eclipses in 1912 and 1911, I think. 1919. No, the first one, they could not do that experiment at that time because of weather issues. In 1915, he corrected that number. He said, no, that's a mistake. This is the displacement. And that displacement was twice that he had shown earlier, and twice that was predicted by Newtonian mechanics. Now, just imagine if the experiment in 1912 had been done, his prediction would have been proven to be wrong. He would have come later on and said, no, I made a mistake. Credibility is gone. So in that sense, Einstein was absolutely lucky that the experiment didn't happen at that time. 1915, he corrected it. 1919, so this is the sort of a picture. So if you had the sun, a star over here would displace much more because the light passes very close to the sun. A star over here would actually have no displacement because light is passing very far away, and therefore you could use this. If Einstein was correct, the apparent location would be shifted by an amount that he has calculated. So, and if the prediction is not borne out, of course, general theory of relativity would have been thrown out of the window. The apparent shift in the process can only be seen during an eclipse. So what was done? So that was what the sun would look like in an eclipse, completely blacked out. So now you can see the stars. May 29th, which is like 4 days from now, this year.
2 days.
1919. This was the experiment that was sought to be performed. And if you see the globe, the path of totality was running right through here. Already they had missed out earlier because of bad weather. So what Eddington, one of the very famous astronomers in UK, he wanted to get this experiment done, but this time they were not going to leave it to chance. They said, we will check it out at 2 different locations. One location was in the Western African island of Principia, which is there, and the other location, Sobral in Brazil, is right there. 2 different locations. So if one location was cloudy and rainy and all that, at least the other one would survive and they would be able to get some data out of that. They did experiments, and it turned out that Eddington's observation during the total solar eclipse confirmed Einstein's theory. The displacement was actually the same as what he had predicted after his correction. So it was quite sort of fortunate for Einstein that they waited till 1919 to do the experiment after he had made his correction, and the theory was borne out to be true. And so here is a situation where a theory subjected itself to a falsification process and was not falsified. The theory doesn't have to be falsified, but it must subject itself to the falsification process. And it turned out to be right. And that's Eddington for you. And mind you, this little anecdote here, Eddington was from England and Einstein was from Germany. And mind you, during the war, these two countries were at loggerheads. But the nice thing was in science, politics doesn't show up. So here was an Englishman trying to verify the predictions of a German whom they were at war with. And that's the nice thing about science, which shows that science really should be beyond politics. The theory subjected itself to a falsification process. It was not falsified though, and Einstein's general theory was proven to be right. And since then, there have been a lot of other observations, and they've all shown this theory to be correct the way it has been proposed. Let me take another example in a case where the theory was falsified. In chemistry, in school, we all learn about this Dobereiner's triads, right? Where we say, before Mendeleev came up with the classification, people were trying to see if there was some method in the madness of all the elements that they had. There were so many elements, there's so many properties. Is there a systematization at all in all of this? So Dobereiner said, I think there is some systematization. For example, if you take we take lithium, sodium, and potassium, he said that's a triad, and it was hypothesized that the atomic weight of sodium, which is in the middle, is actually the average of the atomic weights of lithium and potassium. And here this is a triad. And if you look at that, lithium is 6.94, sodium is 22.99, potassium is 39.10. And if you take the average of potassium and lithium, the average turns out to be 23.02, which is pretty close to what sodium is. So it seems like the Dobereiner's triad hypothesis is correct. At least there's one example. Now enough, you got to check. And mind you, the falsification process of Popper says that even if you find one counterexample, the theory is out of the window. Calcium, strontium, barium. Calcium 40, strontium 88.6, barium 137.3. The average of calcium and barium is 88.7, close to strontium. Good. Third, chlorine, bromine, iodine. Chlorine 35.45, iodine 126.9, bromine 79.9, 81.18 is what the average is. Somewhat different, but that's because of a different problem. Because bromine has two isotopes, and that's what is causing it. But look at this. Fluorine, chlorine, bromine. Fluorine is 19, bromine is 79.9, chlorine is 35.5. And if you take the average of fluorine and bromine, it's 49.5. Nowhere near the atomic weight of chlorine. So the Dobereiner's triad hypothesis is completely wrong in this case. It has been falsified. The moment it is falsified, you look for an explanation for that. That's where you break new ground in science. And then what happens is, of course, today we know why that's the case, because when you go from fluorine to chlorine, there is no intervening D elements. But then when you go from chlorine to bromine, there's an intervening D element which pushes the atomic weight a little further. And that's why the average doesn't work out. We know that today. But at the time of Dobereiner, this was not known. But the hypothesis had to be cross-checked. And the hypothesis was actually falsified in the case of the lower halogens, the chlorine, bromine, and iodine. It works with fluorine, chlorine, and bromine, but not with chlorine, bromine, and iodine. And we know why. And of course, much later, Mendeleev came and he had this periodic table that was set up, and the rest is, of course, history. The point I'm trying to make is, here is a case where a hypothesis was made so precisely that it could be either checked or falsified. It turned out to be right in a number of cases, but turned out to be wrong, at least in one case that I've shown over here. And that is enough. The moment it is proven to be wrong in one particular case, you have to find an alternate hypothesis, or at least find out why it failed in this case. And that is how you make new ground. And that is what I said earlier. If your paper says my data does not agree with existing theory, as I said, it is very hard to publish it, but that is where new ground is broken in science. And after that's the periodic table. Can we hide that thing? Because it is the law of triads, therefore, is falsified. The Vijay not there. It's blocking my stick. If your statement or if your hypothesis, if you make a hypothesis, if you say I have done some research and this is my hypothesis, but your hypothesis is so vaguely framed that you could never falsify it, then it's not a hypothesis at all. It's not a scientific hypothesis. For example,
Oops. What? Start from the- Right on. Right on.
I've been trying. Now, yeah. For example, if I said I'm going to be looking at behavior of human beings, I do statistical analysis of various people, and then I come up with my hypothesis that all human actions are motivated by self-interest. Is that a hypothesis? No, it's an opinion. I could be well wrong. Why is it not a hypothesis? There is no way I can do an experiment to even quantify what self-interest is. So how can I even test this theory? How can I put this theory to a test to either check it out to be true or to falsify it? So this statement can never be falsified. And therefore, this statement is not an hypothesis at all. And this is what I mean by saying that you must propose your hypothesis in such a way that it can subject itself to being verified or be subjected itself to being falsified. Only then it turns out to be a scientific hypothesis. So as I said, there's no way to quantify it. And therefore, the above statement, all human actions are motivated by self-interest. It might look to be true. I don't know, but it is not a scientific hypothesis because it's out of the realm of science. It's just an opinion. How are scientific discoveries usually achieved? What are the various thought processes that go on? Well, one is systematic search for new knowledge. I know A, B, and C. I want to know what D is. So, for example, I'm a chemist. I can think of, I know the properties of the first four acids in the acetic acid, propionic acid, butanoic acid. I want to know what the rest is before I do experiments. That is an incremental increase in knowledge. It's very important because you need all this data. But there's an incremental increase in knowledge, systematic search for new knowledge. And a lot of science happens this way. The other one is flashes of insight. And what do I mean by flashes of insight? Not this. Periodic table, Mendeleev. That was a flash of insight. In fact, if you go back and read Mendeleev's account of how he came up with this, he was plagued by this idea that there must be some systematism in this whole process. And he was trying to work it out, but couldn't come up with any of these, the proper sequencing. And apparently he just dozed off. And he says, in a dream, I saw a table where all the elements fell in place. It essentially meant that he was so caught up with this idea that his subconscious mind was constantly working. And then he seemed to see the table. He got up and wrote it down, flash of insight. And that is how the periodic table was born, a new concept in chemistry. In fact, that's one of the biggest systematizations you can ever think of in scientific history that came out. Structure of benzene. Till the structure of benzene was proposed by Kekule, we knew of straight chain compounds. But benzene's properties and other things did not fall in place. And Kekule was plagued by that idea. He dozed off, and suddenly he says in his dream, in his sleep, he saw a snake holding its tail. And thus he came up with the idea of a circular compound. And this was it. So the concept of structurally cyclic molecules came from this point onwards. So you broke new ground, flashes of insight. Another one, accidental discoveries, which is what we will be talking of today. There's another way by which scientific research progresses. And the last one today is very, very relevant, is collaboration-induced research. And particularly because communication is so good these days, I can talk to my collaborator, sitting somewhere else, or almost on a daily basis. And therefore, collaboration can be extremely effective today, maybe not about 30, 40 years ago. An example is the Emmanuel Charpentier and Jennifer Doudna for their CRISPR technology was collaboration-induced. So today you have collaboration-induced research breaking new ground. And this is how science progresses. Accidental discoveries, and it's called serendipity for a certain reason. It is from a novel, the word Serendipa and then serendipity. We'll not get into that. And I want to make the statement, even though I'll be listing out these things, please keep in mind, in the field of observation, chance favors the prepared mind. Just keep the statement, we will see what you mean by that. And just to a disclaimer, pictures and information that I've got mostly from books and internet sources. So I'm just mentioning it here. In a lot of places, I've given you the source, but in certain cases, I might have missed it. But these are all from the internet and books and so on. moment you talk about serendipity, the first thing that should always come to mind is Alexander Fleming. That was supposed to be one of the biggest breakthroughs in medicinal chemistry that came through sheer accident. And that was in 1928. And how did that happen? Now, Fleming wasn't trying to make penicillin. Penicillin was not known at that time. He wasn't even trying to make penicillin. He was trying to study Staphylococcus bacteria. So he made a culture of this in various petri dishes, put them out there, and it takes time for the culture to grow. So he said, let me go for a vacation and come back, and then I will take a look at it. So he was on a 2-week vacation, and it appears he had neglected to close one of these petri dishes properly. He didn't cover it properly. It's slightly open, which means it got infected. And when it got infected, what happened? This is what it looked like. And you can see what happens. Right here, there's a mold that was growing because of the dirt or some infection that happened. So the mold was growing. But what Alexander Fleming actually observed was right next to the mold, there was no bacteria, clean. But over here, the colonies of the bacteria were growing. So the mold was preventing the bacteria from growing, and it immediately theorized that this mold must be secreting something that is actually killing the bacteria, and that could be the drug that we were looking for. He wasn't trying to make penicillin. He was trying to study Staphylococcus bacteria. This is what I meant by saying when Pasteur said the chance favors a prepared mind. What would most of us, what would we have done? Petri dishes contaminated, you would have cursed yourself, you would have cursed your student, dumped it, cleaned it, gone home, made a new one. He was observing what happened with that dish. And mind you, there was a certain amount of, that's the mold, that's the normal Staphylococcus colony. Staphylococcus colony undergoing lysis, meaning it was just breaking down. And Fleming's observational prowess led him to note that the Staphylococcus was not growing around the mold. So the mold was secreting something to kill the bacteria. He had identified penicillin at that time. The element of luck also favored Fleming. And you will see, just like the element of luck favored Einstein, that the eclipse was not observed in 1912 for various natural reasons. It was observed in 1919. Same thing with Fleming. What was the luck? The mold, the penicillin growing mold, grows well at 20 degrees centigrade, but the bacteria grows well at 25. The Staphylococcus bacteria goes well at 25 degrees centigrade. It so happened when he went on vacation, the first part of his 2-week vacation, the temperatures were around 20. So the mold grew very well and prepared a lot of penicillin. A little later, the Staphylococcus started growing, but the mold was killing it. Now just imagine, if the Staphylococcus had grown first, before the mold had grown, he won't have seen the process. Why? Because penicillin works on the bacteria during its growth process. After it is grown, penicillin can't do a thing about it. It interferes in the cell wall production. So he was lucky that the temperatures were such that the mold grew first and was ready to kill the bacteria when the bacteria started growing. Chance favors a prepared mind, but it has to be a prepared mind. So this is an element of luck. And you will see in this serendipity exercises, there's always a chance of luck that favors them. Fleming considered penicillin only for external processes, and even he did not think of it as a wonder drug. In fact, he was even suggesting that it's a nice way to distinguish between 2 types of bacteria, the gram-positive and the gram-negative, and he didn't go beyond that. The reason being, they could not prepare enough of penicillin to even use it as a drug. That was left to 2 other people, Boris Chain and Walter Florey in Australia. They came up with a method to grow penicillin. And once they came up with this method, penicillin could now be administered as a drug, and it was soon found to be a wonder drug. And for which Florey, Chain, and Fleming got the Nobel Prize in 1945 for the discovery of penicillin and its curative effects. In fact, it was Florey and Ernst Chain who showed that penicillin can be used internally, and it turns out to be a wonder drug. And mind you, these drugs have played a huge role in the treatment of wounded soldiers during the war. Before the advent of such antibiotics, mind you, a small cut could kill you. So once there's a cut, there's an infection would just spread. There is no antibiotic to stop it, and that's what happens. So this was a drug that really saved. And of course, to honor Alexander Fleming, there are a lot of postage stamps and so on. That's apparently the original picture of Alexander Fleming's petri dish. And he says, I did not invent penicillin. Nature did that. I only discovered it by accident. And that's what he says. And just for those of you who are chemistry oriented, this is the structure of penicillin. And the interesting thing is it's got two cyclic structures, two fused rings, which is the backbone of the penicillin structure itself. And it can have various groups over here. It can either be benzyl penicillin, oxacillin, ampicillin, amoxicillin. And when you go to the doctor, they give you all sorts of these medicines. And all they're doing is changing the side chain R to various groups with the different effects and different. And of course, the biggest problem today that we are facing is antibiotic resistance that the bacteria are showing. And very soon, we might just run out of antibiotics. We won't have them to treat this. And that's a big issue today in the medical circle. This is another very interesting story of indigo. And indigo, mind you, is a dye that is used to, that very bluish purple color that you see for dyeing cloth. How was indigo grown before? Well, indigo, the wash-fast dye that's used for navy blue uniforms. And the initial production was through plantations in India. India had the biggest plantation area of indigo. And the British, who were there at that time, were completely exploiting it. They would make our farmers grow indigo so they could use it for their Manchester textile company. And indigo, this is the only way by which indigo was got. So they basically had sway over the dye market at that time. Because at that time, the Germany said, why can't we come up with a method to synthesize indigo, synthetically make indigo and use that? So Bayer came up with a method. Don't worry about it. If you're not a chemist, don't worry about it. It is just a sequence of steps. You start from naphthalene, which is easily available as a byproduct in food distillation. You take that naphthalene and convert naphthalene to indigo. Synthetically, it can be done. They came up with this process and indigo could be produced, and Bayer was making some indigo this way. The problem was the very first step over here, naphthalene to phthalic acid, was extremely slow. No industry likes slow reactions. You want quick reactions that you can make by the tons every day. This reaction was extremely slow, and therefore it was not in an industrially viable process, but it was still a process. They were making it, but not able to compete with the British market that they were holding sway over the Indian farmers. The process was not indirectly attractive because of that first reaction was too sluggish. Now, one day it so happened that when one of the chemists, he was trying to make indigo in a batch, and he had this reaction going, and he needed to stir the reaction. So that was Eugene Sapper. He was the chemist trying to run this reaction, and he was trying to make it. The first step, of course, was slow, so he had to wait. And he felt that maybe if I stir it, it might help. Now, normally a chemist would stir a reaction process with a glass rod. That's the way it is done. I think Sapper was a little lazy, and thankfully so, because instead of going and looking for a glass rod, he just used a thermometer that was already there and started using the thermometer to stir the mixture. Thermometer broke. And the reaction was finished in a jiffy. The moment the thermometer broke, the reaction just rushed. Inadvertently, he had found a way to make that reaction go very fast. And what had happened? Well, the mercury got into this reaction mixture, and that reaction mixture had sulfuric acid, because that's how the reaction is done. Now, because there was sulfuric acid which reacted with mercury, you had mercuric sulfate that was produced. Now, mercuric sulfate was a catalyst for this reaction. So inadvertently, he had produced a catalyst for that reaction, and because of it, that reaction went off in a jiffy. Immediately, what happened was mercury. Yeah, Carl Hyman, who was the chief chemist there, he devised a synthetic procedure using mercuric sulfate as a catalyst for the first process. And then he found that you could make indigo by the tons very, very quickly, because that sluggish process was taken care of. And that broken thermometer, therefore, completely rewrote the history and the economics of the world at that time. Because once these people could make indigo by the tons, Britain completely lost its market. So these were making much more indigo than what the farmers could give him. And therefore, and thankfully for us, because what was happening was the indigo plantations were actually straining us, because we couldn't grow rice, and therefore that was leading to famine and so on. So thankfully, this helps to avert that situation. And you had Bayer completely take over the market as a result of one broken thermometer. So you can see, but again, it is important that Sapper, who did the reaction, Eugene Sapper, moment he broke the thermometer, he didn't panic and throw the sink into the sink. He saw what was happening and he saw that the reaction had grown very fast and therefore realized that I might have inadvertently generated a catalyst. Analysis was done, and that is how this reaction was done. And that's the mercury sulfate catalyst up there that I've now introduced in this whole process. The incident of the broken thermometer completely changed the economic picture. Germany now became the largest producer of indigo as opposed to Britain, who till then dominated the market through their control on India's indigo plantations. This is another very interesting story. I'll just have two more stories. One is this is a conducting polymer. Now, normally when you talk about conductors, what's a good conductor? Metals, aluminum, copper, iron, silver, gold, good conductors. You don't think of organic molecules as being good conductors. But they had this idea that if I have an organic molecule with double bond, single bonds, double bond, single bond, then I can have the electrons flow back and forth, and that could be a conductor. But the question is, how do I make this polymer? So starting with acetylene, I can think of making this polymer. So there were people who were trying to do it, and one of whom was Hideki Shirakawa in Japan, was trying to make this compound. He was taking acetylene and trying to make the polymer, but what happened was he was making a black powder whose resistivity was still very, very high, still not a good conducting polymer. It was like nowhere near what the metals would be. So he therefore was quite annoyed at the whole process. And until one day, he asked one of his visiting researcher, Hyung Pyun, he said, perform this reaction again. I know this reaction has to work, but somehow it's not working. Why don't you try this reaction out? So he asked him to do this reaction. And what was the reaction? He said, there's something called the Ziegler-Natta catalyst that is normally used for these reactions. Don't worry about what that catalyst is. It's a specific type of a catalyst that is used for polymerization. He said, take that catalyst and add a millimole, meaning add a certain quantity, conduct the reaction. Either he didn't hear him properly, or maybe he gave a written note where his handwriting was not legible. The researcher thought he has to add 1,000 times more, 1 mole of it. So instead of adding a certain amount, he added 1,000 times that amount. And what he got was a silvery powder instead of a black powder which they were getting till then. And again, this guy didn't panic and throw it into the sink. He tried to check it. And Shirakawa said, check the conductivity. And it turned out that this conductivity was quite high, much higher. Still not close to the metals, but still high. So they were now moving forward in producing organic molecules that can actually conduct electricity. The big breakthrough came when Shirakawa was working in Europe as a visiting professor, and they made this compound, and they were adding bromine for a very different reason. They wanted to add bromine and remove the hydrogen and make carbon-rich and hydrogen-poor compound. But what happened was the bromine got inserted into it and created holes, meaning conduction holes. And the conductivity of this polymer after treatment with bromine increased by 10 million times. In fact, Shirakawa says by the electrometer which we were using to check the conductivity just broke. It just went off scale. So he said, we broke a machine, but we came up with something very interesting. We came up with polymer that was now reasonably close to metals when it came to the conductivity. And it's just like an order of 2 less if you look at the conductivity of these. But then it was very close to the metals. And these now became a very important commodity, the conducting polymers. And it was essentially discovered through an accident, through a mistake that happened in the lab, very clearly. But again, it was a prepared mind that caught that. But due to an apparent misunderstanding, this happened, and we'll move on. Yeah, that's what I said. When you dope it with bromine, the conductivity increases. Today, these materials are used as LEDs. They have multiple uses. They are good chemical sensors. They are good conducting materials, so you could use it in electronics. They are good. They also have good electroluminescent properties, meaning if you apply a potential, they shine light. They will throw out light, which you can use for, as light emitting materials, and it's become a very useful material as far as materials applications are concerned. Again, for those interested in chemistry, I just have put some structures of these molecules that you will see. And the first one is polyacetylene, which is what Shirakawa made in his laboratory the first time around. The three people, Alan Heeger, McDermott, and Shirakawa, who collaborated at the time and who got the Nobel Prize in 2000 for their work on conducting polymers. And mind you, it essentially came about because of a total misunderstanding between the guide and the postdoc. They just didn't understand what they were talking about. So the point is, there's just not any mistake. A mistake that was combined. I think we should not have the Zoom at this time because that's it is the mistake combined with a sharp observation. Again, the prepared mind, that is extremely important. And Alan McDermott scored, the harder I work, the luckier I seem to become. So the moral of the story is don't be afraid of making mistakes. You might get a Nobel Prize for having made that mistake, which is what happened in this particular case. Gun cotton is again a very interesting story. In this case, Schonbeam was a German chemist who had this habit of doing chemistry experiments in the kitchen. And needless to say, the wife didn't like it because he would make a mess of it. And therefore, there was a strict rule that he couldn't use the kitchen for experiments. But this guy couldn't hold back. So what he would do was when the wife was away, he would go into the kitchen, do the experiments, and by the time she came back, he would clean it up. This is what he was doing. Until one day, what happened was he accidentally spilled nitric acid and sulfuric acid on the table. Now, that's an evidence. The wife comes back, she will know. So he panicked. He looked around to see what he could do to wipe it off. And all he did was he grabbed hold of his wife's apron, cleaned it, but now this has got wet. So he has to dry it before she came back to leave no evidence. So he put it near a heater close by so that it would dry up. And to his amazement, he found what happened was the apron disappeared in a smokeless flash of fire. Boom, it just exploded. No smoke, it burnt away. Now the apron is gone. So now he's in big trouble. But he didn't panic. He said, oh my God, what is this really happening? There is some chemistry that I'm missing. Essentially, what he had done was he had nitrated cellulose and it had become nitrocellulose, which is an extremely good explosive material, which is what he discovered. And of course, I think he did make some money in that. And I don't think his wife had any problem with him working in the kitchen after that. And
Action that was full of shock.
full of shock, exactly. And that's the little structure for those interested in chemistry, cellulose with nitration at certain points, and gun cotton was actually discovered. So there's and mind you, again, he was lucky. Had he only spilled sulfuric acid or only nitric acid, he might not have seen this. He spilled a mixture of nitric acid and sulfuric acid, which is the nitrating mixture. And therefore, the reaction worked. In every single case that these things happen, there's always this element of luck that goes along with it. But mind you, the luck seems to be favoring the prepared mind anyway. And that's the point we're trying to make. This is about the shatterproof glass, which we have in cars. The windshield, when there's an accident, the windshield doesn't spray off. It just stays there, but it shatters, but it stays there. Well, it was discovered quite interestingly in 1903 by a French chemist by name Benedictus. And what he was doing was he was reaching out for a glass flask kept on the top shelf. It was empty and he wanted to use it, so he reached out for it. But when he pulled it out, it slipped and fell down. What happens to a glass vessel when it falls? It shatters into 100 pieces. It shattered, but it still held the shape like that. The shape was still there. And he was wondering why was this happening now. It turned out that the person before him who had used that had used some polymer film and collodion, which he did not wash properly. So the film made a nice, the polymer made a nice film on the inside. So when the glass beaker broke, the film was holding it. And therefore, it did not shatter. It broke into pieces, but did not spray away. And that is how laminated glass was accidentally discovered. He didn't know what to do with it at that time. But until he read about an accident about a young girl who was badly injured because of the sprayed glass. And then it occurred to him, what if I put this over there, and therefore you have laminated glass on cars? So two accidents, one in the lab and one on the road, together contrived to bring you this laminated glass. And that's how it was done. But of course, the car companies at that time did not want to take it because it was extra cost. And they said, safety is not our problem. Safety is the driver's problem. He or she should be driving safety. We can't be helping it. But later it became today it's a regulation. You have to have glass that is laminated as a safety procedure. But it came as a result of a very interesting accident in the French chemist laboratory of Benedictus. I'll just tell you one more and then we'll move on of Teflon. Teflon was really mind-blowing. It was discovered by Roy Plunkett, was a young PhD, and he was given the job of making alkanes as a refrigeration material. So he was making this he was making fluoroethylene and then trying to chlorinate them and use that and study the properties to see if it can be used as a refrigerant material, as a safe refrigerant material. Today, of course, we can't use that because it's got a different problem with ozone depletion. But when he tried to do that, and what he did was he would prepare tetrafluoroethylene, a compound, and fill it up in canisters. And anytime he wanted to do an experiment with that, he would take that canister, take out a certain amount of the gas, fill it up in his glass vessel or something, and do the experiments. But he was a very systematic guy. Every time he filled this canister, he would weigh it. After releasing the amount of gas for his experiment, he would again weigh it. So he had a record of how much gas he was actually taking out every time. Very systematic guy. One particular day when he was doing this experiment, that's for me, alarm. One particular day when he was doing this experiment, it turned out that the canister, no gas was coming out. What does that mean? No gas, empty. So what will you do? Keep it aside, take the next canister and do your experiment. Not Plunkett. Plunkett said, I'll weigh it. The weight was exactly the same as he left it last time. So the weight is the same, but the gas is then coming out. So he said, oh, maybe there's a valve problem. He changed that. Nothing. Same weight, no gas. He couldn't. Apparently, the others in the lab are telling him, come on, get on with it. Take the next cylinder, start the experiment. He said, no, I have to understand. Why is there no change in weight, but no gas is coming out? So he just cut open that little canister. And inside he found slippery white powder. What had happened was, because of the inside surface, or whatever it was, the tetrafluoroethylene had polymerized to give polytetrafluoroethylene, which is Teflon. So he had accidentally made Teflon. And that is the reason why the weight was still the same, but no gas was coming out. And then he said, he found the properties. As a chemist, he said, let's see what the properties are. And what are the properties of Teflon? It doesn't dissolve in any solvent. It doesn't react with acid or alkali. It doesn't conduct electricity. It was soft and slippery. The most uninteresting compound you can think of. It doesn't want to react. It doesn't want to dissolve. Nothing whatsoever. It doesn't want to conduct electricity. Just sitting there. So Plunkett didn't even know what to do with it. So he just took that powder and kept it aside, saying, we'll see. At least we know what happened. So we'll see that later. It so happened at that time, mind you, there was this, and that's your structure of Teflon for those interested, the inertness. There was this Manhattan project going on at that time, mind you. And America was trying to make the bomb. You know, Einstein, I'm sure many of you have seen the movie Oppenheimer. You would know. They were trying to make the bomb. But to make the bomb, you had to get uranium-235. So you do isotopic enrichment. To do isotopic enrichment, the way it is done is you convert uranium to uranium hexafluoride, UF6. And the fluorine compound of uranium is extremely reactive. So when you try to do the separation by diffusion process, the membranes were being eaten away by this compound. So they couldn't do the separation, which is hampering their progress. So they didn't know what to do with this. And apparently the big boss of DuPont, where Plunkett was working, and the army chief, the one in charge of the Manhattan project, they were discussing, he said, this is a problem we have got into, and we don't know what to do. He said, no, I have a material. Somebody has discovered that, which is totally inert. Why don't you take that and make gaskets or membranes of that and see what happens? They made membranes of and gaskets out of Teflon. Uranium hexafluoride could now be isotopically enriched and the bomb could be made. And that is how the Manhattan Project actually worked. And I always close the story by saying, had only Plunkett not cut open that cylinder that day and not discovered Teflon, Japan would have saved itself. Japan would have been saved. But you know how things work. One little cut of the cylinder and boom, Japan is completely exploded. And of course, so what happens is there was a French engineer by name Gregory who said, can I apply a small amount of Teflon on my fishing gear so that it's because it's slippery, you know, I can roll it quite easily for my fishing expeditions. And his wife said, why are you doing that? Why can't you put it on a pan and see whether you can make nonstick? The nonstick pan came from the idea of Gregory's wife.
Nice.
So he made that. And today, of course, Teflon pans, you know, the industry is a huge industry. And I don't think there's any kitchen today which does not have a Teflon coated pan at all. I will skip this because we've already run out of time. So I will just skip this. And this is, of course, a very interesting experiment of Rayleigh and Ramsay, the discovery of inert gases. And I use this to essentially show how good researchers know their numbers very accurately. You know, for example, when they say the weight of the gas is 2.3102 plus minus 0.002, they know what numbers are accurate, what numbers are significant, and so on. That's very, very essential. That's why I use this. But I will skip this. So I would like to go ahead and the list of happy accidents goes on. X-rays, saccharin, vulcanization of rubber, textile dyes, Perkin, radar. Many of these were discovered quite by accident. And therefore, you can see that accidents have a very important role to play in the progress of science. But again, there are many things that contrive to make these successful experiments. One, luck. In every single case, you see that something went in favor of these people. But all said and done, the important thing is that these people had a prepared mind. They were willing to expose or explain or, you know, look through, try to explain the mistakes that they had made and trying to discover new ground in scientific research. This combined with curiosity, a keen sense of observation, and a very analytical mind. Not mind. So don't waste a good mistake. So if you do experiments in the lab and you make a mistake, check it out. Don't waste a good mistake. Don't waste a good accident. Because it's very often you'll see that accidents can actually provide you very useful breakthroughs in science. So chance does favor the prepared mind. I just want to, this is again a nice quote, which I quite like. Okay. The seeds of great discoveries are constantly floating around us, mind you. As I say, you know, I mean, when you look at the folklore, Apple was supposed to have fallen and Einstein, I mean, Newton was supposed to have discovered gravity. Apples have always been falling, but it takes a very prepared mind to catch it. That's what it says, that the seeds of great discoveries are there forever floating around us. But it's only the prepared mind that catches it and discovers it. I'll just say a few words because it's important. There are many youngsters over here as to how science must be actually practiced. Hallmarks of a good science. Be published in a good science journal. Anybody who goes to a newspaper or a press conference to report his results, I don't think I will even want to listen to that. That's publicity. That's not science. It must be subjected to good peer review. Sound scientific methods must be used in the study. Multiple experiments. Don't do one experiment and report it. Cross-check, cross-check, cross-check. In fact, Ramsay's experiment, which did not explain, actually is multiple methods to determine the same parameter. Unbiased sampling procedures, if you're doing statistical analysis of data. Large sample sizes. Adequate control experiments. These are all hallmarks of good science. Clear description of scientific methods. Don't hide anything when you report your experiments. Let people repeat your experiment to check whether what you're saying makes sense or not. That's good scientific practice. Adopt ethical practices. Appropriately credit co-workers and collaborations. And pre-existing data must be properly cited. Avoid confirmational bias. And what do I mean by that? Very often before we do an experiment, we think that the results are going to be the following. Don't get too much wedded to that idea. Because what can happen is your results might be trying to tell you something else, but you will completely ignore that because that is not falling in line with what you're thinking. So you must beware and keep away from this confirmational bias. For example, if you did experiment and you got these data points, that's a good line. And what about that little point out there? Oh, it doesn't fall in. So what do you want to do? Now the data looks even good, much better. Cheating. There was a point that fell out and you're trying to suppress it. What's the best way to take care of that? Repeat the entire experiment to see if that outlier is really an outlier. If it consistently happens to be an outlier, then it simply means that at that value of B, your system is trying to behave differently. It's trying to teach you something. Listen to it. Therefore, don't throw away data just because it doesn't fit with your hypothesis. And that's what confirmational bias is. And that's very important for scientists to guard against such confirmational bias. What is the responsibility of the scientific community? The responsibility to ensure that only sound scientific ideas are propagated. In the process of rigorous peer review, mind you, sometimes new and brilliant ideas will be thrown out, will not be accepted. If you want to understand that there are many such examples, and that could be a talk by itself. Dan Shechtman, quasi-crystals. He was in fact ridiculed when he came and said that there can be five-fold symmetry in crystals. Who was ridiculing him? No less than Linus Pauling. Linus Pauling said that's all crap. It can't be true. In fact, in one conference, Linus Pauling even said that there are no quasi-crystals, there are only quasi-scientists. He was ridiculed to such an extent. It was only after Pauling's death in the early 90s that his theory started getting the attention. And then it was found that what he was saying was absolutely true. There are crystals which have order but are not periodic. And they have five-fold symmetries. Broke new ground and with very interesting properties. Shechtman got a Nobel Prize in 2011 for what he had just done. But when you come up with new ideas, that's what I have said earlier. If your experiment is not in line with existing theory, it's very hard to publish it. But if you stick your ground, if you're right and you stick your ground, you will essentially come up with new discoveries in the whole process of scientific research. What does scientific reasoning provide for you? Well, first, it guards you against false narratives. The moment you have a scientific approach, you don't accept things, they are just stated. You want evidence, you want proof. You don't spread rumors. That's important. It provides you with a wider vision. And let's see what we mean by that. This is not my concept. It is Gottfried Skad's, who in his article that I've shown here, talks about this, that science provides you with a wider vision. And what is that wider vision? If you ask somebody, what's the time scale that you can talk about? You will say, well, I can talk, I know my grandfather, great-grandfather, maybe about 200 years or so, and some mythology and so on. And then on the shorter side, maybe a tenth of a second or a hundredth of a second, Olympics gives you, that's about it. But you look at what scientific research can do. You actually, in science, you talk about attoseconds, 10 power minus 18 seconds, the time scales of electronic motion and molecules. And what is the long time? 15 billion years, the age of the universe. So you really are thinking in terms of extremely short time scales of 10 power minus 18 seconds to some billions of years. Large dynamic range that comes to you when you start looking at scientific knowledge. What about space? Well, the smallest that most people would tell you is my width of the hair to the longest distance I can think of, which might be some few thousands of kilometers. But in science, the smallest diameter, the sizes they can think of are atomic scales, femtometers. And what's the largest distance you can think of? Well, 10 power 27 meters, which might be the dimensions of the universe. Again, look at the dynamic range. 10 power minus 15 meters to 10 power 27. That's the time space range that you can think of. Mass, electronic mass, 10 power minus 31 kilograms. And large mass, 10 power 53. Maybe the mass of the universe. Again, huge dynamic range. So what science does for you is it helps you to think big. Extremely small to extremely large. You have a huge dynamic range in the properties, in the measures of these properties that you deal with. Teaches you how little we are in all this process. So there's a certain humility that comes in when you have this. Science also teaches you to admit you're wrong. You'll see many scientists, there are so many lectures that I've given and so many times I've said, I don't know. I'll have to find the answer or whatever. It's very often you'll see a scientist who's willing to accept that I don't know, because I know there is so much to know. I can't obviously be knowing all of it. And that's where the humility part comes in. So I was wrong, a statement that you will often hear from scientists. Doing science is great fun. I've enjoyed every bit of it the last many decades that I have done science. But with joy comes a huge responsibility as an individual, as a member of the scientific community, and the society at large. So that's a responsibility that as a scientist you have. Thank you. And that's my email. You have any question that you want to talk to me about later, you can always contact me at that. I'll be more than happy to have a discussion with you. And now if you have discussions, any questions or comments or anything that you want to say, I'll be more than happy to address it. I didn't say I'll be more than happy to answer it. I'll be more than happy to address it.
Sorry, I will put it off. Okay, first let us thank
Check.
for scientific interesting talk. We have time for some questions. And other questions for the. Okay. So from the audience to questions. Yes, go ahead.
So, Viswanathan, we're talking about falsification.
Yeah.
And you said that the existing community, I don't know, existing community is always putting a damper on people who are trying to do this. But the existing scientific community is putting a damper on people trying to do this for their own reasons, whatever reasons be, because this guy is trying to falsify something.
Yeah.
Yeah. Now, if with this kind of attitude, would it not hamper the zeal of a young person who wants to get ahead in science?
Yeah. Let me clarify what I said, but what you say has relevance. I didn't say that the scientific community is essentially trying to prevent you, but there is a, let us say, if I say that light travels in straight line, we know that. And now you come up and tell me, like Einstein said, no, it actually bends. Without any change in the density of the material, it bends. I'm not talking about refraction and all that. It's bent due to gravity. That's a change in the hypothesis, in the whole theory. People may not accept that, and therefore they will try to revolt. They will try to ask for more proof and so on. But as he said, in the case of Dan Shechtman, big scientists like Linus Pauling saying that your theory is wrong made it very difficult for Dan Shechtman to even take his idea to the community. In fact, he was thrown out from his lab. He was thrown out from his lab because they said, we don't want you spoiling our reputation. You coming and telling us that there's a 5-fold symmetry in crystals. Apparently, the director of that research group gave him a crystallography book and said, go read this first. To which Shechtman said, yeah, I've read that book, but what I'm saying is not in the book yet. So you're right. The community does not, very often it is not, it's not personal. It's not that you come and say something and I want to put you down. But it's just that I don't think you're right because I know this is true. No, you're saying something very different. And unless I'm completely convinced with all the experiments, so you'll have to wait for a long time before adequate experiments are done. Somebody else does the experiment and proves that your experimental methods are right.
By the extent of your knowledge, and you don't accept new knowledge. Is it right?
You are reluctant to apply. I won't say you don't accept because all these theories were finally accepted. Dan Shechtman got accepted. He got a Nobel Prize for it. As they always say, when you come up with a new idea, what are the various thought process? First, ridicule. They will laugh at you, saying that, crap. Then they will be hostile to you. Like Pauling said, there are quasi-scientists, but not quasi-crystals. That was insulting. And in a big conference, after he finished his talk, this is what Pauling said. And when Pauling says that, the community believes, because Pauling had his stature. So it was very difficult for Shechtman to do that. And after that, after the ridicule and the hostility, then comes mild acceptance. Maybe this guy is saying something that's okay. Let's check it out. And then acceptance. And then accolades. He gets a Nobel Prize.
Have the kind of resilience.
You must have that. You must have that resilience. You will be tested. If you are a good scientist coming up with new ideas, you will be tested. But that's where that sets apart the good, resilient scientists from the not so good and not so resilient.
Classic example is Chandrasekhar in 1936, when he actually discovered the stellar evolution and also possibility of black holes being. He was ridiculed by the same person,
Eddington.
He ridiculed him and he didn't get a job at UK. Unfortunately for him, UK had fantastic scientists like there are various big Nobel laureates were there. They were not prepared to go against Eddington. So he shifted to US, and it took several decades for him to get the recognition which he deserved. Finally, he got the recognition. He also got the Nobel Prize.
So that process is there. Ridicule, hostility, mild acceptance, acceptance, and then
Stop.
and then accolades finally. But you have to put through all that.
Okay.
Mentioned, yes, the major unfolds and secret solid from prepared mind.
Yes.
Could you elaborate on that? Prepared also like in our review.
Yeah. See, all the experiments I showed, mind you, in every single case, the person who did the experiment was alert to what he was seeing. That he was not seeing what he expected to see. He was not expecting to see those results. It would have been very easy for that person to throw away the result and then start all over again. Like Fleming could have just thrown away that petri dish and start all over again. Penicillin is gone. Or Eugene Sapper, after he broke the thermometer, panicked, threw everything away. That catalyst is gone. The prepared mind concept comes in where that person says, "Oh, look, I made a mistake, but let me see what happens." That's the prepared mind thing. And when you start exploring that, that's where you get new ground. In fact, I didn't quote one, the saccharine discovery. If I get in a prepared mind, this guy works in the lab. And what are you supposed to do after you work in the lab, before you go home? Supposed to wash your hands. This guy didn't do that. He went straight home and sat down for dinner. The wife brought something, he ate, and then it was very sweet. And he told her, apparently, what is it today? Your dish is extremely sweet. She said, look, don't try to be too romantic. This is the same food I make every day. So he said, no, it's really sweet. And then it occurred to him, that might be something that I made in the lab that stuck to my fingers. He went back to the lab and he did another stupid thing, which you're not supposed to do. He licked the compounds that he was actually had made that day. One of them turned out to be saccharin. Prepared mind. And that's how saccharin was discovered. Of course, today we don't use it for other reasons, but that's how it is.
Okay. Other questions? Yeah, people. Yeah, go ahead.
Happened in early 1900s. And if you start plotting a graph of the number of experiments like such accidental discovery, it is progressively declining. Why do you think this is happening?
No, don't go by the fact with what I just shown you, because I showed you a very, very small subset of the number of experiments. Maybe all these books will tell you of many more experiments. But see, the Sheckman work that I told you, Dan Sheckman's quasi-crystal, was again, he was just looking at aluminum niobium or aluminum manganese compounds under a transmission electron microscope. Routine experiment, and suddenly he found that there was a very different pattern that he was seeing. And of course, he wrote in his notebook, tenfold symmetry, cross, question mark, question mark. This happened, of course, in the 1990s, I think, or 1980s. Quite by accident, because he was trying to look for the properties of aluminum and manganese compounds for some other reason. But out popped this quasi-crystal concept, which is extremely revolutionary. So that happened in the last, let's say, 50 years ago and so on. With all the interesting discovery that happened in the last 10, 15, 20 years, they will have to stand the test of time and they will show up maybe later. I don't know.
Normally, insulators you do not have. So metals you do not have.
They become superconductors.
Yeah. Yes. I think Kamaling-Hahn's experiment to begin with.
Unusual discovery.
Yes. I think it was with mercury. I think he got that. Mercury at very low temperatures.
You suggest some books,
There are
school when the teachers teach science, if they bring in here and there that.
No, it's always important when you teach this thing to bring in anecdotes.
Yes.
In fact, I was just telling my colleague there, when I teach the very first undergraduate courses, which is, in Mohali, it used to be like 200 students. And I also always say, when you teach 200 students, you're not teaching 200 students. You're not a teacher. You are a performer. You must go on stage and perform for them.
Yes.
Only then you can catch their attention. And one trick I used to adopt was I would get all their birthdays on very first day itself. And on every particular day, when it was someone's birthday, I would call up that person and have the class wish that person a happy birthday. And then I would mention some scientist born on that day and talk about the work of that scientist and all that. I think it's sometimes quite inspiring to know that your birthday coincides with Schrodinger, or it coincides with Pauli or something. It's very nice. So, in fact, it so happened that, it so happened that one particular time, it was, I think, August 27th or something. It happened to be Schrodinger's birthday, I think, and there was one boy in the class who happened to have that birthday. So I called him out, Abhishek Goswami, told him this is what it is. And then I told a little bit about Schrodinger and his work. Few months later, the students came and said, "Sir, why did you say that? Why?" I said, "What happened?" "No, he already thinks he's a theoretical physicist." I said, "Good, that's the whole point." But at the end of the story, he's now doing theoretical physics somewhere.
Some kind, great.
Okay.
Yeah.
There is a question.
Scientists are freedom to fail, so they don't understand it. So they have shade funding for their contamination. But today we follow some standards, we need to put some right thing to do a particular thing. In that case, we don't have is the city or
Accidents are less.
No. See, no. The protocols in science were always there. They were there. They are there. They will be there, and accidents will always happen. So it's just that I don't know. I told you I will say I don't know. So today I have a chance.
One of the greatest things about that is people were looking through the radars. Radio from this thing. They were looking at the antennas. And it was giving some wrong answers. They found out that there was a pigeons who laid something, and then that shit was there always. So they cleaned it up and found the famous what is known as the cosmic microwave background radiation was there in that place. So accidents do happen in the other way also.
The protocols in science have always been there, that you do a science in a certain way. So I did mention that very loosely. It's there. But there will be people who will break away from protocols, who will lick their fingers after they come back from the lab and discover something, and so on. So that will always be there. And regarding, I really can't answer that question whether the incidence of such accidental discoveries has come down, because for that I will have to sit down and make a list of all the accidental discoveries that happened from time immemorial to now, and then maybe plot a graph. Maybe somebody who is doing scientific history can take that as a problem.
You should also have the courage to say something is wrong.
Yeah, I know. Yeah. No, but that book may not have all the recent ones.
Batman is a archaeologist. He is actually discussing the idea. It is
Yeah.
ultimately only in science or any.
No, it can happen anywhere. It can happen in social sciences. It can happen anywhere. Yeah, in cooking.
Yes,
I'm very sure,
we get good dish.
you forget to add something and your
No, you should.
people say, "Oh, that's very nice." And then you will know it's very nice because you forgot to add something.
Meeting someone, that's your right partner. Serendipity.
That's a different. Good.
Yeah.
Okay. So I think we probably will wind up. And after this.
I hope I didn't exceed my time.
No, it's okay. It was interesting. They are not complaining. Let me ask.
Sir, one question.
Yeah.
It's first time I'm attending. It looks like 73rd. 74th one.
74th. Okay.
We have such a different recorded.
Yeah. There is a YouTube channel. There is a YouTube channel we have.
Yeah.
Which all the popular science lecture series.
So what is the
Science lecture series?
science lecture series?
Lecture series. Yeah.
All 70.
Yeah, all of them are there. Of course, there's some problem of how good the thing, like for example, a lot of interruptions like there.
It's okay.
That's okay.
Subject and content is good for all.
Okay.
Sir, very smart idea comes when you're not doing a regular work. So
No, I think it could. No. I think what happens is, if you are seized of a problem, you keep thinking of it 24/7, not consciously, but somewhere back of your mind. Very often you'll see people who are into this. Suddenly they'll go into a trance. They're not listening to you. So in the back of their mind, there's something else going on. And when those things happen, I believe the subconscious mind processes the whole data. And suddenly you have a spark, like it happened for Mendeleev, or it happened for Kekulé and so on.
Many philosophers also say beyond time and space. I think that is beyond time and space.
But what is,
Many philosophers, spiritual people tell you beyond time and space.
science is different from spirituality. I will make it clear. So space and time are there, there is some, and some limit is there, and the space is expanding also. That much is the thing we know. Now, if you're asking whether there was time, before the Big Bang, etc., these are all, one can conjecture and make a hypothesis. But simple like him, you will ask, what is the proof? How will I falsify it? How will I check whether it is correct or not? All those questions, people will pounce on you. So you have to be, one has to be very careful.
In fact, one of the students came and asked me once, can we talk about the speed of velocity? Can we talk about the speed of time or something? I said, speed is anything, change in quantity with respect to change in time. What does it mean to say change in time with respect to time? I said, I don't even understand how to answer that question. But apparently there are books which talk about such things. I'm very sure if I read that book, it'll take me quite a while to understand what the hell is going on. But
Speed of time.
yeah,
Is relative.
speed of time.
Time is relative.
Time goes slow, time goes fast,
Yeah,
all that.
time
What
is
do you
relative.
mean by that?
If you go at a very high speed, the time also goes very slow. Yeah.
So, before going to my duty as a board of thanks, I want to make some couple of points. So anybody wanted a participation certificate, scan this QR code and you will get it. If you are already registered, you will get it.
Only for college students, we want to display that they have access.
And we are offering as a complimentary copy some past issues of Tullir and Tullirism Tamil and General Mantra. So please collect it. And if you have